Okay, good. All right. So yeah, so I'm going to talk to you about the development of coffee schemas, and I want to mention that this is not my talk. This is Maksym's talk. It's his project when he did it as a fellow. I'm just giving it on his behalf because he can't attend the event today. Um, the context is in the context of coffee, and we have a tutorial of a long an hour tutorial later in the week on coffee. Is that coffee basically takes a root file, nano-IOD, Fizzlight, some different types of formats, and gives you back an awkward array. But it doesn't give you the awkward array in the same way that uproot some tree dot arrays would give you. It restructures the array in a way that's meaningful to do physics. So how does it do that? The way it does that is through something that's called the Coffea schemas. And the schemas basically describe how to take this array from the root file and how to restructure it when giving it back to the user. And that's a core functionality of Coffee's nano events, basically. Um, so Coffee implements different schemas. They all inherit this inheritance graph, and they all inherit from a base schema. And we have support for different things like Nano AOD schema, Fizzlight, Delphi schema, Tree Maker, and like from Nano AOD schema, we can make particle flow Nano AOD, scouting Nano AOD, and so on. And all these schemas describe different ways to restructure this awkward array. Okay, the idea was make it a separate package. Many people want to restructure awkward arrays, and there's one, maybe they shouldn't live inside coffee. You don't, if you want to restructure an awkward way in a meaningful way to you, maybe you shouldn't use coffee. Maybe it should be a separate package. And two, the way it's currently implemented in coffee is that it uses some sort of domain-specific language, and it's very hard to extend the schemas, and it's very hard for the user to implement a new schema if they want to, because it's using a very complicated piece of machinery that's internal to coffee. So the whole idea is make it a separate package and make it much simpler. So this was the whole idea of Maksym's fellowship and the project, and Awkward Zipper was born. And I put links here for the package and its documentation. It's very preliminary at the moment, but I'm just going to give you a brief presentation on it. So the advantages are a smaller package, only a few dependencies. It only depends on NumPy, and Number, and Awkward. And it's number one, it simplifies how the schemas work internally, and it makes it easier for users to create their own schemas. And the reason for the simplification is that internally right now, what Coffee would do is it would take only the structure of the array without holding any data, and a mapping to the current structure of the array to the branches in the root file, and try to change the mapping and the structure of the array accordingly using a very specific domain specific language, and to give you back this restructured array. And awkward zipper, what it does is it takes in an awkward array and gives you out an awkward array. And that's the simplification mainly. And this is the current plans of development. And the development worked in this way. The first goal was to make Nano UD format work with eager materialized arrays. Then Nano UD format works with virtual arrays. These happen. Eager and virtual modes are tested and and documented. This has happened. And we're currently at the first release in a way. And now it's only tied to Nano UD, but then the next steps are Awkward Zipper supports all the schemas from Coffee. And Coffee then uses Awkward Zipper instead of its own schemas, basically. So Awkward Zipper is a dependency of Coffee. And then in the future plan is that all the new schemas that people want to write are developed on Awkward Zipper directly, and not in Coffee anymore. So I will go on and do a short demo of what actually happens. So what you normally have in Coffee is you have this factory, this nano events factory. You say whether you want to load from root, and or whether you want to load from Parquet, and so on. With Zipper, there's no such thing. With Zipper, you just load something and you load it with uproot. You open a tree, and you just say dot arrays. Have the arrays back, and you can show this. And you'll see that, for example, if we look at the event number 0, we'll see that we have different branches like electron eta, electron H over E, and so on. They're laid out to you in the same way that uproot would give you. Then you import nanoAOD because this is a nanoAOD file from Awkward Zipper, and you say that you want to restructure the array. Okay? And this is something extra just to show it better. And now the array has been restructured. And if I now look at this result, and I do result.fields, sorry, result.fields, now the structure is different. Now I don't have all the branches laid out, but I have things grouped up. I can do like result.jet, and this behaves like a particle. And then I can do .jet.pt. And then I can add jets together and they behave like a 4-vector. So I get back a 4-vector. So I added all the jets to themselves. Yeah, so I can do these sorts of things. And this happened only because I just applied this schema. So the array has been structured in a meaningful way to do physics. And I get also the nice thing that particles behave like particles and they can be added together and so on. Okay, the main point, I will not stick a lot into this, is that the fields internally, instead of using this domain-specific language, is awkward array to awkward array operations. So if I import two internal functions from Awkward Zipper, you'll see that these functions act on some things of the array. If you look at array.localIndex here, sorry, did I miss this? Array. Oh, sorry, I need to define this. Yeah, my bad. And array dot local index, we'll see that, yeah, this is an awkward array, basically. That's all it is. So these internal functions work awkward array to awkward array. So that's the main point. There's no domain-specific language. Awkward array to awkward array operations. And yeah, as I explained, things are grouped up together, like flat arrays remain flat arrays, like run, PS weight behave like a jagged array, but although it has a fixed number of elements per row. Things are grouped up together, like generator, and you have generator.id1 and so on. And particles are grouped up together and behave like particles, like result.jet. And you can do things like result.jet.mass. So we have extracted this restructuring functionality from Coffea and made it into a much smaller package that's easier to maintain and easier to extend, and gets us all the same benefit of the same array structure, but it's much nicer to the user, number one, and to extend it. And finally, what I want to mention is that Zipper also works with virtual arrays. So what happens right now is that we have this transition towards using virtual arrays in Coffea. So virtual arrays is just basically lazy loading. So you don't load something until you actually need it. So you don't load events.jet.pt, but you load it when you do events.jet.pt times 1, let's say. So this is going to be in the next release of Uproot, this virtual equals true thing. So you can lazily do tree.arrays and you can restructure it with Zipper. And we have this access log that keeps track of the number of branches that we accessed. And you'll see that if we look at the access log at this point, it's empty. If we look at something, result or result.jet, you'll see that there's a bunch of question marks here because it's unloaded and the access log is still empty. But now, when I start doing math, let's say I just recreate the array again, and I start doing the simplest z-peak that I can think of, and I take all the possible pairs of muons, and then I can look at the access log. You'll see that they access the n muon branch, because this is the only thing that I needed to know, the number of muons in each event to do all the possible pairs. And then I can add the leading and the subleading of the pairs, the first and the seconds together, as 4 vectors, and I can calculate the invariant mass. And because it's a small root file of only 40 events, well, I only have 6 right here. And I can look at the access log right now, and you'll see that what I eventually had to access are the muon kinematics, PT, phi, eta, mass, and charge. And this is because I need to do this 4-vector addition, and this adds PT, phi, eta, mass, and charge together. So Zipper supports lazy loading. And yeah, this is all I want to show of this demo. And the hope is that we will at some point, maybe hopefully soon, support for all the coffee schemas apart from NanoEOD, and this will be the main way to restructure awkward arrays. Yeah, that's all. Thank you.